What if everything people think they know about Machu Picchu is only the surface of the story, quite literally? For more than a century, Machu Picchu has been celebrated as one of the greatest engineering achievements in the ancient world. Its terraces are admired for their beauty, their symmetry, and their practical genius. They are usually described as agricultural platforms that helped the Inca grow crops on steep mountain slopes while controlling erosion, stabilizing the land, and channeling away rainwater. That explanation sounds sensible, and for a long time it seemed complete. But beneath those iconic terraces lies something far more complicated. Hidden under the visible stone steps is a deep structural system so extensive that some engineers now estimate as much as 60% of Machu Picchu's construction is actually underground. That is not a minor support of feature. It is an enormous hidden foundation network, and its scale raises a serious question. If the terraces were meant only for farming and basic slope stabilization, why was so much invisible engineering necessary? The moment researchers began studying the site more closely, the usual explanation started to look too small for the evidence. Machu Picchu sits nearly 2,400 meters above sea level on a narrow ridge between steep drops. To a modern engineer, this is not an ideal building site. It is almost the opposite. The slopes plunge sharply on both sides, and beneath the surface lies fractured granite that is constantly shifting. Add to that an annual rainfall that can approach 2,000 millimeters, and the result is the perfect setting for landslides, slope failure, and destructive water pressure inside the mountain itself. In simple terms, Machu Picchu was built in a place where a city should not have lasted. And yet it did far more than survive. It remained stable for more than 500 years. Early visitors and explorers, including Hiram Bingham in 1911, treated the terraces as mainly agricultural. Flat land was scarce, so the Incas seemed to have cut farming steps into the mountain for crops such as maize and potatoes. That interpretation felt straightforward and practical. But once engineers and archaeologists began examining individual terraces in detail, the idea of simple farmland started to fall apart. These terraces are not just shelves of dirt piled against the mountain. Each one is built as a carefully layered system. And that same system is repeated across more than 700 terraces with remarkable consistency. At the base sits a layer of large stones, leaving open voids through which water can move. Above that is a thick layer of gravel that acts like a drainage channel, allowing water to spread laterally rather than build pressure in one place. Above the gravel lies a layer of finer sand that filters the water and prevents the topsoil from being washed down into the lower levels. Only then comes the fertile upper soil where crops could actually grow. Seen from above, it looks like agriculture. Seen in cross-section, it looks like engineering. That distinction matters because the terraces behave less like ordinary farming steps and more like a repeated filtration and stabilization system. Their layered design is so standardized that it resembles controlled construction rather than local improvisation. This is not what one would expect if the only goal were simply to make enough flat ground to plant crops. The scale of the labor makes the mystery even harder to dismiss. The Inca moved immense amounts of stone, gravel, sand, and soil up a mountain without iron tools, without wheeled vehicles, and without large draft animals. Each terrace had to be built in sequence, layer by layer, across the mountainside. That means hundreds of thousands of tons of material were transported and placed deliberately. This was not casual agricultural effort. It was organized, large-scale construction on a level that feels closer to a mountain-wide engineering project than to ordinary terrace farming. And the location itself only deepens the puzzle. Machu Picchu sits between two fault lines, exactly where underground stress and water movement are most concentrated. Geological surveys show that this area is under constant pressure, with groundwater moving through cracks in the granite and weakening the mountain from within. That means the site's main challenge was not just steepness, but internal instability. It was already a stressed landscape before the Inca began building. This is the contradiction that changes everything. Why would a civilization choose one of the most unstable, water-saturated, landslide-prone places in the Andes and then build one of the most durable stone cities in human history right on top of it? The deeper researchers looked, the less accidental the site appeared. One of the most revealing clues came from the behavior of water itself. At Machu Picchu, rainwater does not simply rush down the slopes the way it would on an untreated mountainside. Instead, it disappears into the terraces, where it is absorbed, filtered, redirected, and quietly moved through the structure. Even more striking, water continues to move through parts of the site even when there is no rain falling. The channels and fountains are not dry systems waiting for storms. They remain active, fed by a source that appears to emerge from within the mountain. The Inca built a sequence of 16 fountains stepping down the slope in controlled succession, with each fountain feeding the next. The design is so precise that variations in pressure and flow are stabilized as the water moves downward. This suggests that the system was not built only to provide water, but to regulate it. And the primary spring that feeds these fountains emerges from the fault zone above the city itself, meaning the Inca were tapping groundwater already under pressure inside fractured rock. That detail changes the terraces from passive architecture into something more dynamic. If underground water was continually building pressure inside the mountain, then the terraces and drainage networks may have been designed not merely to support farming, but to intercept, redirect, and relieve that pressure before it destabilized the entire ridge. At that point, Machu Picchu stops looking like a city placed on a mountain. It starts looking like a system built to manage one. That interpretation becomes even more compelling once the hidden water system is taken seriously. At first glance, the fountains and channels of Machu Picchu seem decorative or practical in a straightforward way, as though they existed only to supply drinking water or add beauty to the city. But engineers who studied the site found something more unusual. The water flow through Machu Picchu is too stable, too controlled, and too persistent to be explained simply as runoff from seasonal rain. Even during drier periods, water continues moving through the site. That immediately suggests a subsurface source rather than a surface one. The spring feeding the famous sequence of fountains emerges directly from the fault zone above the city. It does not come from a visible river. It does not depend entirely on rainfall collected on the surface. It appears to be part of a groundwater system continuously recharged inside the mountain itself. This matters because groundwater moving through fractured rock is not a harmless background detail. In a mountain already cut by faults, internal water can build pressure, weaken the rock, destabilize slopes, and trigger collapse. In other words, the Inca were not just building on a mountain. They were building on a mountain that was hydraulically active from within. Once that fact is acknowledged, the terraces begin to look less like agricultural conveniences and more like part of a mountain-scale pressure management system. Their layered structure could absorb rain, prevent topsoil loss, and support cultivation. But it could also do something more fundamental. Intercept water before it concentrated dangerously. Slow it down, spread it laterally, filter it downward, and reduce the buildup of pressure within the slope. What looks like farming from the surface starts to resemble hydrological control when viewed in cross-section. The same logic applies to the city's placement. Geological mapping has shown that Machu Picchu sits directly on intersecting fault lines. These are not insignificant surface cracks. They are deep structural fractures in the granite, zones where the mountain has already split and shifted over time. For a modern engineer, this would normally be a warning. Faulted terrain is precisely the kind of terrain most builders would try to avoid. But the Inca did not avoid it, they aligned with it. Researchers have noted that the orientation of walls, stairways, terraces, and drainage channels often follows the same directional patterns as the underlying fractures. That is too consistent to dismiss as coincidence. It suggests that the builders understood where the mountain was already weakest and where water was most likely to travel. Instead of fighting those conditions blindly, they designed in conversation with them. This is where Machu Picchu begins to look less like a city imposed on the landscape and more like a city grown out of an intimate reading of the landscape. The faults were weaknesses, but they were also guides. They told the Inca where the rock moved, where groundwater rose, and where stress accumulated. The city's alignment with those patterns implies not ignorance of geological danger, but a deliberate use of it. That same principle appears in the masonry. Machu Picchu's stonework is famous for its precision, especially in the finest structures where blocks fit together so tightly that even a thin blade cannot be inserted between them. But the real significance of that precision is not only aesthetic. The stones are shaped to lock together without mortar, allowing slight movement during earthquakes without catastrophic failure. The walls do not resist every tremor rigidly. They flex, settle, and hold. This is not the kind of solution one develops casually. It reflects a deep understanding of how a mountain under stress behaves. The Inca did not need iron tools, wheeled transport, or modern surveying equipment to grasp this. What they seem to have had instead was generations of close observation, refined building practice, and a highly disciplined construction system. The unfinished blocks in nearby quarries support that idea. Archaeologists have found repeated shaping marks and consistent methods that suggest standard procedures rather than random trial and error. The same forms, angles, and finishing patterns appear again and again. That implies shared technique, training, and transmitted knowledge. Machu Picchu was not improvised by genius individuals on site. It was built by teams, working within an established engineering tradition. The terraces themselves also appear to have helped shape the local environment in ways that go beyond drainage and slope protection. At that altitude, conditions can change rapidly. Strong sunlight during the day gives way to sharp nighttime cooling. Mist moves in and out. Moisture levels fluctuate. Frost can damage crops. Yet the terraces seem to moderate some of these extremes. Stone absorbs heat during the day and releases it slowly as temperatures drop, because each terrace contains deep stone and gravel layers beneath the cultivated surface. It can store and release heat in ways that reduce sudden temperature swings at ground level. In effect, the terraces help create a buffered microclimate. Studies comparing terraced zones to nearby non-terraced slopes have found differences in moisture retention and temperature stability. The terraces hold warmth longer, reduce frost risk, and stabilize growing conditions. This means the terraces were not single-purpose constructions. They were doing several jobs at once. They stabilized the slope, they controlled drainage, they reduced internal water pressure, they created cultivable surfaces, and they helped regulate local temperature and humidity. The more closely the system is studied, the less it resembles a simple answer to one problem, and the more it resembles a multifunctional environmental machine. That multifunctional quality is one reason some researchers have started asking whether the conventional interpretation of Machu Picchu is too narrow. If the site were only a royal estate, or only an agricultural center, or only a ceremonial city, much of this hidden infrastructure would still feel excessive. The hidden system seems overbuilt if judged by the visible city alone. And that brings the mystery into sharper focus. Over-engineering an ancient construction usually means one of two things. Either the builders were compensating for a danger outsiders have underestimated, or they were pursuing a purpose broader than the one later observers assigned to the site. In Machu Picchu's case, both possibilities may be true at the same time. The city may have been designed not only to sit on the mountain, but to actively manage the mountain's instability year after year. If so, then the terraces are not just support structures beneath the city. They are the city's deepest purpose, made visible in stone. What makes Machu Picchu so extraordinary is not just that it stands on a mountain, but that it stands on a mountain that should have failed. By every ordinary expectation, the site is badly chosen. It sits on a narrow ridge cut by faults, saturated by heavy seasonal rainfall, and built over fractured granite that is constantly under stress. Modern engineers would look at such a location and immediately see the risk of sliding slopes, internal water pressure, and long-term instability. Yet the city did not slide, fracture, or wash away. It endured. That endurance may be the most important clue of all. For centuries, people admired the visible parts of Machu Picchu: the elegant terraces, the carefully fitted stone walls, the stairways, the temples, the ceremonial spaces, and the dramatic setting above the valley. But the more modern researchers study the site, the more it becomes clear that the visible architecture is only the outer expression of a much larger hidden system. The terraces are not simply steps cut into a hillside. The walls are not simply beautiful masonry. The channels are not simply decorative waterworks. Taken together, they form a coordinated response to a mountain that was already unstable before the first stone was set. That changes the entire meaning of the site. A city normally adapts to a location in order to survive there. Machu Picchu seems to go further. It appears to have been built to regulate, stabilize, and continuously manage the conditions of the mountain itself. The terraces absorb and filter water. The deep stone and gravel layers relieve pressure. The channels guide flow before it can accumulate dangerously. The alignment of the structures with the underlying fault directions suggests not ignorance of geological weakness, but detailed knowledge of it. The city behaves less like a settlement sitting passively on a slope and more like a carefully engineered environmental machine. This helps explain one of the most unsettling aspects of the site: the disaster that never happened. In many parts of the Andes, mountains with similar rainfall and fractured geology experience landslides, slope shifts, and structural damage over time. Villages disappear, hillsides fail, entire sections of terrain change shape. Yet Machu Picchu remained unnaturally stable for more than 500 years. No catastrophic slope collapse erased the ridge. No major terrace system gave way in the manner one might expect from such a precarious location. That absence is not normal. It is evidence. Some engineers now argue that the greatest achievement of Machu Picchu is not what the Inca built above ground, but what they prevented below it. The hidden drainage system, the layered terrace construction, and the fault-aligned design may all have functioned as a passive, long-term stabilization network. In that interpretation, the real triumph of Machu Picchu is invisible. It lies in the fact that the mountain did not fail. That makes the labor behind the site even more astonishing. Machu Picchu was built in the 15th century under Pachacuti, without iron tools, without wheeled transport, and without large draft animals. Every stone, every basket of sand, every load of gravel, and every layer of topsoil had to be moved by human effort alone. And not just moved, but placed in the right order, at the right angle, and in the right relationship to water flow, load distribution, and slope behavior. This was not the sort of work that produced immediate rewards in an obvious way. A road gives visible access, a wall gives visible defense, a palace gives visible prestige. But much of what was built into Machu Picchu created benefits that were delayed, indirect, and long-term. Stabilizing a mountain means preventing a future collapse that might happen years, decades, or generations later. That implies an unusual way of thinking. The builders were not only solving problems for themselves in the present, they were solving problems for the future. This is one reason Machu Picchu may have served more than one purpose at once. It could still have been a royal estate. It could still have been ceremonial. It could still have supported agriculture, but those labels no longer feel sufficient by themselves. The site seems to have been designed also as a demonstration of mastery over difficult terrain, a place where the Inca proved that they could take one of the most unstable environments imaginable and force it into long-term balance. The microclimate evidence strengthens that interpretation. The terraces do not merely control water, they also influence temperature, moisture retention, and air movement. Stone layers absorb heat during the day and release it at night, reducing thermal extremes near the soil surface. Terrace walls act as windbreaks. Their spacing affects how cold air and moisture move across the slope. Studies have shown that terraced zones can maintain more stable temperatures and better soil moisture than nearby untreated slopes. In effect, the Inca were not only shaping land, they were shaping conditions. That means the terrace system was doing several jobs at once: hydrological control, slope stabilization, agricultural support, seismic resilience, and microclimate regulation. The more functions assigned to the system, the more reasonable its enormous hidden scale becomes. What once looked like overbuilding begins to look more like integrated design. The precision of the stonework also belongs to this larger logic. The fitted blocks of Machu Picchu are often admired as art, and rightly so, but their deeper purpose is structural intelligence. The walls can move slightly during seismic events and then settle back into place. That flexibility is one reason Inca masonry has survived earthquakes that damaged later buildings in the same region. The city's precision was not ornamental excess, it was performance. What makes all of this especially impressive is that it was achieved without the tools modern people usually associate with this level of exactness. No steel drills, no concrete pumps, no laser measurements, no written engineering manuals in the modern sense. Yet the site reflects repeatable methods, consistent geometry, and deep environmental understanding. Some of that knowledge may have come from simple devices such as plumb bobs, alignment cords, and water levels, but tools alone do not explain the site. What really explains it is observation refined over generations, an engineering tradition rooted not in abstract theory alone, but in close attention to how stone, slope, pressure, and water behave. That may be the real lesson of Machu Picchu. The Inca did not conquer the mountain by ignoring its dangers. They succeeded by reading them accurately and designing with them rather than against them. The city's walls, terraces, and channels do not feel like acts of defiance. They feel like acts of understanding. And that is why the old interpretation no longer feels complete. Machu Picchu is not just a beautiful mountain city with clever terraces for farming. It is a deeply layered system built to manage one of the most unstable building sites imaginable. The hidden foundation, the drainage structure, the fault alignment, the thermal buffering, and the seismic flexibility all point toward a design philosophy far more ambitious than simple cultivation on a slope. So when people look at Machu Picchu and admire the terraces, they are still seeing only part of the achievement. The real masterpiece may be the part that was never meant to be noticed. The buried stone, the invisible drainage paths, the filtered water, the relieved pressure, the long prevention of collapse. The terraces are not just steps on a mountain, They are evidence of a civilization that understood the mountain well enough to keep it standing. That is the deeper story now emerging from the evidence. Machu Picchu was not merely built on difficult terrain. It was built as a system for controlling that difficulty, quietly, constantly, and with astonishing success. In the end, the greatest mystery of Machu Picchu may not be how the Inca carried stones up a ridge. It may be how clearly they understood the hidden forces moving beneath their feet, and how completely they designed a city to answer them.